Good morning, good afternoon, wherever you may be on this lovely day. We're going to do a little bit of a challenge today. So I'm going to do a couple variety of analysis problems. So this is actually fairly realistic, which, as you know, the closer you get to realistic usually means a little bit more complicated, and you'd be absolutely correct. So let's talk about analysis as two prongs. Prong number one is to take some kind of sample. This could be a rock, your blood, an ore, a sample, an unknown, an aliquot, some word that's not CO2, H2O, hydrocarbon, hydrogen peroxide, something that i.e. is not a chemical. It's a rock, a sample, a fluid. Certainly things composed of chemicals, but not an individual chemical. So this is really what you got to determine when you're doing these analysis problems. Am I looking at a single chemical? Or am I looking at an impure thing that I'm trying to get a mass percent or purity reading, or what would that be? We're going to start with the single chemical because that's a little bit easier, and then the next video will go into the samples that are a little bit more complicated to deal with. And yes, one of these will be on your test. I do like to push you guys, see what you know, see if you can apply what you need to in a more realistic setting. So, again, these can be a little bit tricky. We're going to start with combustion. Let's do that. So, if I was to describe the word combustion to a 6-year-old, I would probably just use the word fire. So just to remind you, combustion means lighting something on fire. What it means from a chemical standpoint is adding oxygens or oxidizing it completely. So if we were to take a standard, what your car does with gasoline, for example. Gasoline is a hydrocarbon. Hydrocarbon meaning made out of hydrogen and carbon. And we are to burn it in your car engine. We bring in oxygen, and the oxygen and the carbon combine, and the most oxygens we can stick on a carbon is 2, so we get carbon dioxide out of tailpipe. Hydrogen, we can only put really half an oxygen on each hydrogen, or 2 hydrogens on each oxygen, depending on your point of view, and we get water out of our tailpipe. So this is ideally what's coming out of our tailpipe, and this is what's going in. Of course, we can burn things that aren't just hydrocarbons. We can burn things made out of carbon, hydrogen, and oxygen, for example. Alcohol, sugar. This is what your body does for metabolism. Adds oxygen in, and much like your tailpipe, I'm breathing out from my metabolism. Oxygen on the carbon, which is carbon dioxide, and oxygen on the hydrogen, which is water, and then some of the oxygen here helps along. So, same general process, this combustion process. So how are we going to go about this? So, we burn something. We know how much we burn. That's easy enough. You just weigh it out. Light it on fire. We can have some kind of collector for CO2. Figure out how much CO2 we get. Have some kind of collector. Figure out how much water we get. So that's the general gist of this. And this is complicated enough. I want to talk about what's going on chemistry-wise before we do the math, and then we'll do the math. So, all of the carbon in the CO2 is coming from our sample. All of the hydrogen in our water is coming from the sample. So if we can figure out how much carbon we have, and relate it back to the beginning, we know the carbon. If we can figure out how much hydrogen, relate it back to the beginning, figure out how much hydrogen, we can determine what we started with, at least empirical formula-wise. So, of course, going from chemical A to chemical B requires us to use a excellent mole-to-mole ratio, which we can only get from a balanced chemical equation. So our balancing here is going to be a little bit slightly different than what we've done in the past. It's easier to show mathematically than talk about here. And then we can do the super hard one. Or we have the carbon, the hydrogen, and the oxygen. Same idea. Take the carbon and the carbon dioxide, convert it back to carbon in the beginning. Take the hydrogen in our water, convert it back to hydrogen in the beginning. If I have my mass of carbon, my mass of hydrogen, and I take that from the total mass, which has carbon, hydrogen, and oxygen, and take away the carbon and the hydrogen, I'm left with just the oxygen. Get the mass of oxygen, convert everything to moles, divide them all by the smallest number, I have my whole number ratio and my empirical formula. Okay, so what would that look like? So, this is written about as plainly as possible. A 1.5 gram sample of a hydrocarbon produces 4.4 grams of CO2 and 2.7 grams of water to determine the empirical formula. So, you're feeling overwhelmed. This problem's hard. Where do we start? I don't know, but Dr. Werl keeps saying if all else fails, convert everything to moles, so let's just do that. Awesome, good idea. And way to listen to me. That's much appreciated. And I got more than one number. I don't know which one to start with, so let's just do both. Awesome. Rolling along. Okay. So, convert it to moles. And again, these formula weights, they just come off the periodic table, and it's always a bunch of grams per 1 mole. I am now thoroughly assuming you're good at this by this point in the semester. And we have our moles of CO2. We don't want moles of CO2, we want the carbon and the hydrocarbon. So what's that relationship look like? Every time I burn or create 1 CO2, how much carbon did I need at the beginning? Pretty simple. It's a 1-to-1 ratio. 1 carbon atom, 1 CO2. Same thing with the water. Every time I do a water, how much hydrogen did I get? Well, that's, only slightly less simple. There's 2 down there. So 2 hydrogens. And this is all we need to do at this point. We can just plug this through, get some numbers. And I get 0.0, well, no, my sig figs, 0.100 moles of carbon. And down below, I get 0.300 moles of hydrogen. And if we want the lowest ratio, probably don't even need to do math. You can tell it's 3-to-1. But we should divide everything by the lowest number. So I'm going to divide everything, remember, by that smallest number. And I get left with 1 carbon to every 3 hydrogens, or my empirical formula would be CH3. So that's how you do a combustion analysis problem. That one's pretty straightforward. I don't think that's bad at all. Oxygen's a little bit trickier. What would that look like? Wonderful question. And I'm glad you asked it, because we're all set. It's like I have ESPN and I can read your mind. Alright, so a 0.2500 gram sample of a chemical made of carbon, hydrogen, and oxygen is burned to produce 0.3364 grams of CO2 and 0.1500 grams of water. Determine the empirical formula. So, really, the beginning of this problem is identical to what we just did. Take our numbers, convert it to moles, convert that to carbon, and we got to go one step further this time and convert it to grams, which is not bad. And we're going to do the exact same thing with the water. And I know I'm going fast, but this is identical to what we just did. Grams to moles, mole to mole ratio. Remember, we're trying to find the original sample, so that's why we do the carbon and the hydrogen, because that's what actually comes from the original sample. And then we have to do one extra step of the formula weight. So let's see what we get. And I get 0.09999 grams of carbon. And I get 0.01678 grams of hydrogen. If I add those together, I get 0.1168 grams of carbon and hydrogen. Now, we would need to figure out the oxygen. So this is where our starting point comes in. So we know we have 0.25 grams of carbon, hydrogen, and oxygen. So if we subtract out the carbon and the hydrogen, we should be left with just the oxygen. And I get 0.1332 grams of oxygen. Last step is go back to moles. So this is just like we were doing the mass percent problems. And we had grams of carbon, grams of hydrogen, grams of oxygen converted to moles. Zero 0.008327. Sorry, I'm going to round up with my sig figs. The hydrogen, we're basically going back to the previous step and just stopping here. Now we're back to what we were doing originally in the first problem. .008325. 9.15 times 2 divided by 18.02 and 0.01665 hydrogens. Divide by the smallest number, 0.008325. We're going to divide them all by that. And see what we get. We're obviously going to get one carbon. Um, 2.000 hydrogens. And 1.000 oxygens. So we don't have to do any fractions. We don't have to do any of that. I obviously, I guess I made this problem easy. It's not particularly easy, but it could be one more step. And my final answer would be CH2O. So this could be glucose, for example. Would give you that ratio at the end. Again, that's the empirical formula, not the molecular problem. So that's the combustion. I know that was long, a lot of just cranking out math, but that's literally what you have to do. Grams of carbon, grams of hydrogen, add them together, subtract them from the total. That gives you grams of oxygen. Convert everything to moles. Divide by the smallest number. Look at your whole number ratio, see if you have a decimal, and if you have to do fractions and multiply through. If not, you're done. Write it clean, circle it, pat yourself on the back, feel good about the day, and celebrate chemistry. Peace out.